Hello fellow engineers and welcome to Hydrology Engineer. Now this is marketed not really as a game but more as a learning simulator. It's made by a company called Carlson who, as far as I can understand, make actual engineering software like CAD and stuff. And anyway, it's meant to be super realistic, so realistic that you can actually learn about hydrology and engineering. And since I was a drainage engineer for 10 years of my life, I should be pretty good at this, right? Anyway, let's get into a new game and see what this is all about. I've just got the demo because, well, I looked at the game. Not only did it cost $150, but you also had to sign up loads of information and put your personal detail in. Seemed a bit scammy to me, so we're just trying the demo for now. I'm still not quite convinced I haven't just downloaded a virus directly aimed at myself, but we'll see how it goes. All right, so is this this is the game. I thought this was like a loading screen. This is actually the game. Oh my god, whoa, we can move fast. Whoa. Oh my god, I'm in the woods. How far does this go? Oh no, now I think I've broken it. Hang on. Right, okay, so I think we've been tasked with trying to drain this little residential area. Now, generally what we'd do in real life, if we were, let's say there's no drainage there now for whatever reason, some reason it was built without drainage. Why? And we've been tasked to put drainage in. So I guess for now we just do check design. Now it did say it's going to run a 1 in 50 storm. Although it looks like it won't let me run anything until I add a bit of drainage. So that's slightly annoying. I wanted to see what the current situation was. But still, first thing we'd do, we'd probably hire a surveyor to go out and just give us the lie of the land. Whether that's done through a LiDAR survey, which is sort of done from a drone or an aircraft, and basically they just scan the ground. You get a rough sort of indication of what the grounds are, or a topography survey, which is probably what you've seen people on the side of the road, with tripods. They look like they're doing important stuff, but really they're just marking on points and levels and stuff. And basically once you've done that, they allow us to have contours. Ooh, lovely. Oh, this is taking me back. So if I look at this, I'm going to imagine, because as far as I can tell, there's no numbers on these. Usually you'd probably have numbers on these contours, or at least on every 10 or something, just to tell you roughly what level it is. Oh, actually, look, I got coordinates down the bottom. Now, contours are they're the elevation, is the level. So as I sort of hover my mouse over here, I can see from that point, the Z number gets lower and lower, meaning as expected, there's a high point down the middle of the road. Perfect. That's what you would expect. Because that allows, as water falls in the form of rain, lands on the road, it should all go to the edge of the road, and that's where we collect it in our gullies. So if we head back up the road, this is going to be our high point here. So 256.891. And so if we look at this, you can see any water that lands, it will either go down the road that way, or it will come around here. And look, that will be a low spot. So first thing you sort of want to do as a drainage engineer, you want to check out where all your high spots are, where all your low spots are. So we've got one there. If you look, because these contours are going that way, we can tell the road's going down to there. So that's going to be a low spot because the contours on this side, they're doing the same thing, but in that direction. So we got low spot that side of the road, low spot that side of the road. And then over here, we've got 2 more low spots there, and then that up there will be high point. Decent. Now, why do we care about low spots? Well, think about it. Drainage is just water flowing downhill, really. So low spots are where your water's going to collect. So if we don't put an outlet there, that's going to be a big puddle, and it will never drain. It will just evaporate over time. Oh, look, there's actually toggle show. Oh, it actually shows the low points. So was I right? Those two. And then over here, that one. Yes, we got all the low points. I'm a genius. So that's cool. We'll turn that off. What else do we have up here, actually? Oh, run storm event. Oh, yes, it does actually run it. Exactly what I said would happen. All the rainwater came to the low points. So we've got a big old flood there. Now, a flood in sort of drainage engineer terms, it's just a puddle. But basically, this road is now flooded there. It's probably flooded at the other low points. So yeah, there and there. So that is decent. I'm actually loving this. This is my old day job, but in a video game. However, I have just found this button, show water flow line. And basically, if I click on that, that will show how to read contours if you're a drainage engineer. So basically, because I've done this so often, I can tell if a raindrop lands there, it's going to go that way against that wall and then along that edge to the low point. If one were to land, let's say there, it would go that way, hit that curb, and then run along this edge all the way down to that low point up there. But this button allows you to see that without actually having to know anything. So that was roughly my first one. You can see it goes directly to the curb, always perpendicular with a contour, because perpendicular with a contour, that's basically downhill or uphill, depending on what way you're looking at it. And then the other one I said, did I say like up over this way? But look, you can see it goes perpendicular. I mean, that's not actually, let me go from above. That's not actually very realistic. Developers, if you're watching, either your contours are wrong or your weird thing's wrong. I mean, to be fair, it's not bad, but I guess to like make a surface with like really smooth points. I think basically this surface is probably triangulated like with loads of like triangle pieces, because you can sort of see like the line changes when I get to each one. So you can sort of imagine. Can you see like where my mouse is moving? Like, everything downstream doesn't change. I'm guessing because where it does change, like there, along this edge, there's like the edge of like a triangle, and that's basically how surfaces are made. But yeah, essentially what I said sort of works. I was a little bit more accurate than the PC, but whatever. Anyway, if a raindrop were to land there, it would go straight against that curb and then flow all the way down there, following the curb line, and it goes to the low point. So yeah, quite useful tool that, but generally we'd just use this to sort of work out where the high and low points are. And the reason why this tool is useful is because it allows you to make catchment areas. And basically each catchment area, it's like working out the area that contributes to each low point. So this low point up here, you can tell only the water like on this side will end up over there, because any water that comes down like this edge, for example, goes all the way down to that low point. As we just saw, the ones over this edge go all the way down to that low point. So I think the sort of orange, they're like the boundaries of each catchment. Yeah, and you'll notice each of those catchment areas, they don't just include the road, because you've got to think about stuff like people's driveways, people's lawns, just like grass verges in general. Now in the UK, when we're talking about like grass, like a verge area contributing to the amount of water on there, we apply a 0.3 ratio. Because basically we're just assuming that 70% of the water that lands on the grass will just soak in, 30% of it will run off the top and contribute to like your road drainage. Whereas with like tarmac, with like hard paving and stuff, it's just 100% of the area contributes. And you need to know your areas so you know how big your drainage runs are going to be. All right, anyway, let's turn off that water for now. And let's create a storm network. So storm networks are made up of various parts. You've got your surface water catchers. So like over here, we've got like a grating, which is pretty common in the UK. You've also got these like curb inlets, which we don't really use in the UK, but in America, they're pretty common. So if we like roughly plop that down, you can see what they look like. Yeah, if you've ever watched the movie It, I think that's what the clown was hiding in. I think that's why we don't have them in the UK. They're a bit too scary. But in the UK, we just have these gratings, which we would call a gully. Now, when I designed the drainage for a city in Qatar, I had to manually design, as part of a team, but I had to manually design 30,000 of these gully placements. So I had a big spreadsheet, and basically every gully, you could tell how much water was going to it, where it was located, all that sort of stuff. Bonkers. Anyway, there's sort of two ways to calculate drainage in terms of like where your gullies want to go. There's the easy way, which like local council will sort of use, and then there's the more in-depth way that like the big highways authorities use. Not sure what way this game's going to go, if I'm honest, but let's do the simple way for now. Now the simple way is you just say each gully can take a maximum area. So what you do, you'd start with a gully at the low point. So boosh, that goes in there. You then got your next gully and you'd shove that upstream so that your contributing area to the downstream gully won't be too big. Now I don't know what the game's showing me with the blue area. Perhaps that's the area it recommends, like the max area it can take. In which case, you'd shove your next gully like upstream, say there. But then you'd have to do one over the other side. Now, because this is the demo, I think I can only place 2 of these gullies. I may have to spend $150. I need more than 2 gullies, game. But with both of those in, they are going to be taking like a specific area. Hopefully most of this. Actually, no, I don't know what the blue area is, because it doesn't go all the way up to the high point. But basically, let's just delete that other gully. I've just got the one gully at the low point now. If I click on this, you can actually see like loads of information about it. Ooh, including the drainage area, which, oh, look at all this. Oh, look at this. Here we go. Sorry, I'm nerding out here. So you can see of the area contributing to this. It's worked out each of the areas in meters squared for every different material. So asphalt, which is tarmac, that's 335 meters, and the coefficient is 0.9 rather than 1, as I said before. It's saying that 90% of any water that lands on the tarmac will make it to the gutter. 10% will probably get will permeate through it like into the ground, so like won't contribute to your drainage network. So a little bit less than the UK, not a smaller safety factor, if you will. We've then got the lawn, the grass, as I said earlier, 0.3. Oh, they've used 0.2. So again, less water contributing from the verge than how we do it in the UK. And I'm guessing because this is made by an American company, these are probably the American standards. Now they've also got building, forest floors, all different ratios, concrete curbs and driveways. So the curbs, which are like these bits, because they're made out of concrete, not asphalt, they're not as permeable. So they've said 95% of the water that lands in it will contribute. Now, to be honest, the top of a curb is such a small area. I'm guessing it probably includes like this width, which we don't really have in the UK. But it wouldn't really be worth splitting out. Like you're really going into detail there. Remember, drainage is just based on probability anyway. Like you don't know how much it's going to rain. So you don't really need to go into that much detail. You're better just to play it a little bit safe, spend a little bit more money. And hopefully when you find out the probabilities of the storm were like way under what they should be because of global warming, your road won't flood as often as it would do otherwise. Anyway, so basically we use the rational method. So we've got those runoff coefficients, which are basically just all those times by the relevant areas. So that gives us our sort of, I can't remember the name of it. All the knob jokes I do on YouTube, it's actually knocked away my drainage knowledge. The effective area. So that gives you the effective area when you multiply your runoff coefficient by your drainage areas. So it's not the total area, it's the effective area, like the area of water that we think will actually make it to the gully. You then times that by your rainfall intensity, which is in millimeters per hour. And basically that changes depending on where you are in the country. And as I said before, it's all based on like probability, using historic data, trying to project that forwards. But for example, like Wales is a lot wetter than like England. So if I was designing something in Wales, the rainfall intensity would probably be a lot higher than it would be in England. Anyway, so that's our area contributing to this gully. The thing is, once the water gets to that gully, assuming the area we've allowed to go to it is okay, the water will enter the gully and then it's just trapped in like a concrete box under the ground. So from there, we need to take the water to other places. Now, you can see up here, the depth of our structure, 1.2 and a little bit meters. That's a value you use all the time in the UK when you're doing like pipes under the ground. Because basically, if you have a pipe that's under a road, the safe depth above that pipe is 1.2 meters. So from the top of the road up here, if you go underground to like where a pipe is, you can have 1.2 depth or deeper, and the pipe won't need to be covered in concrete to protect it like from the traffic above. If your depth was shallower than 1.2 and your pipe's under the road, you have to encase your pipe in concrete just so it can withstand the weight of like cars above it. So from here, we've got to take our water from the gully underground in pipes to an outlet. Now, an outlet would generally be either a pond or like a river or something like that. I don't know what we actually have on. Oh, look, is that a pond? Yes, we have a pond. You can tell by the contours. It's completely flat at the bottom. And then it's got like slopes around the side. Probably 1 in 2 slope. Yeah, 1 in 2, maybe 1 in 3. And if in case you're wondering, the slope of the earthworks, this bank, depends on what the soil is like. Generally, it'll be 1 in 2 or 1 in 3 for a pond. And ponds can either be used to like store the water so that you can limit the flow out to a river, or this could be just like a sort of soak away area. So your water goes in here, and then because it's nice and spread out, it just drains into the ground over time. So what we want to do, we want to find a route from this gully to that pond using as few manholes as possible and a short drainage run as possible. But you gotta think about various things. So you have like a max distance between manholes. So if we go from this gully, you can see we've got a manhole there. You've probably seen these like on the ground. Basically, it's just like a steel lid, and if you take that off, it allows you to get down to the pipes.
Really?
So if we just go from above, well, we would be connecting our entire network to this, but I think what we'll do in this case, rather than digging under everyone's drives and stuff, because remember, if this pipe gets blocked, you got to dig it up if you can't fix it. So we'd probably shove one either slightly up or slightly down. Let's go slightly down of the junction. And then from this point, you might think, well, just do the next one in the road up there, Matt. We could, but it's worth noting, remember this road, that's the high point up there, so it's falling this way. So by putting our pipe run against the grain, it's going to be getting deeper and deeper. And the deeper your pipe is, the more expensive it is to build. So we probably don't want to put that one there. What we can do, though, we can move it. And we got two choices. We could either go to like save there and then do a straight run down to our pond, or we could go down that road. I think for now, let's just go from there. We'll go from here down to there. You can see, with the length, we're probably okay to go straight into the pond. So what I want to add now is something called a head wall. Now, a head wall is basically just a structure that allows you to outlet, like, from under the ground, like, into the pond in this case. So you can sort of see what it looks like there. And depending on how low we do this, because we've got a manhole at a 1.2 meter depth, you can see the slope as I go down the hill. Now, it's worth noting, the steeper your pipe is, the faster your flow is going to go down it. So if you had, like, this at the bottom like that, a 1% grade, your water's going to absolutely cream it down there. And then when it flies out into the pond, it's going to start like eroding this. So it's probably worth sticking with the 0.1% grade we've done and doing this like a bit higher. You can't actually see them on here very well, but there's a load of stones we've molded underneath. Again, that just helps with like erosion. So it's like a stone bedding for the water to run down into the bottom of the pond. But yeah, so we've made our first little drainage network. So if we run a storm event, we can see exactly how this works now. So you can see up the top of our drainage network. Oh dear, it is surcharging. I think there's too much water down there. We may need to increase our pipe sizes. But in terms of just generally how it works, you can see this large area that was flooded before. There's now only a small strip of water. And generally that would be called a flow width, because as the rain's landing, remember it's coming along this edge before it enters the gully down there. But because this is bubbling up, are all my manholes doing that? Yeah. Yeah, if you ever see a manhole lid doing that, something's gone very wrong. Now, I think what's happened, man, there seems to be so much water on here than there was last time. But I'm going to guess what's happened is either you can size your pipes, and I've done them too small. Yes, look, you can change your diameters of the pipes. Oh, decent. Okay. You can also change the material. That's cool. In the UK, generally, we work in plastic. So I'm just going to go along and change all these pipes to plastic. The main difference between concrete and plastic, in terms of like how the water flows down it, it's just like the roughness coefficient. Is that in here? Yeah, your Manning's number, your roughness. So generally your concrete and your plastic will have a different one of those. But in the UK, we like to use plastic because they're nice and cheap to replace. Whereas a concrete pipe, if that breaks, like it's a lot more work to try and fix. So when you're sizing your pipe network, generally you'd start downstream and you'd pick a pipe size. I mean, shall we just go up one? So we'll try the 450. So I can apply that to every single pipe run. So we're just increasing the diameter, how round the pipe is. So if we run the storm event again, that might be a bit better now. Yes, I think our pipes are big enough because the gully is no longer surcharging and the manholes look fine as well. Decent. So basically we made the pipe bigger so that more water can fit down it. And because the water can fit down underwater, it's no longer like bursting up through the manholes and stuff. So that's now the right size in terms of under the ground. But remember what I was saying earlier about the easy way and the hard way of knowing where to put your gullies. So you'd always have them at a low point. Generally you'd have a double gully at the low point as well, but whatever. We've just got a single one. But the more detailed way, the complex way, is this flow width that I mentioned before. Basically, in your design storm, like the worst storm you design against, which I think is a 1 in 50 year storm. So the storm that should only happen once every 50 years. As I say, it's all probability. It can happen twice in 1 year, but it could still be a 1 in 50 year storm because it might not happen for another 100 years. But what you would do for that storm, which is what we've got simulated here, we'd want to ensure that this flow width isn't too big, because basically if this goes beyond whatever distance you want there, generally where a car drives to the edge, because you don't want cars driving through puddles. If it exceeds that, then you need to put another gully upstream to lower it down. Because you can see at the very top, against this curb, this is the very top. So there's only a small amount of area contributing. Hence, there's only a small width of water here. As we run down this curb, remember more and more areas contributing. So the width of the flow gets wider and wider. You can measure from the curb what the flow width is. In the UK, I think generally you go for like 1.2 meters, I think it was. So this is exceeding that. So what we'd do from the high point, we'd go down to wherever 1.2 happens. So like there, say, and that's where we'd put another gully. I mean, hopefully this will actually do that. If I put a gully in, I mean, annoyingly, there's not a curb there, so we'd just do it upstream of that driveway. But if we shove that in there, we've just got to connect this to a manhole, so we'll shove that down there. So I've just run the storm again, and now you can see exactly what happens. So as before, the flow width gets wider and wider. Once it gets to that 1.2 meter width, that's where we put our gully in. So all the water that was against the curb goes down into the gully, into your pipe network. And then downstream of that, because there's no area contributing to that, the flow width is really narrow again, and then slowly gets wider and wider until you get to your low point. Again, if it goes over 1.2 meters, you'd put another gully in. So generally, that's how that works. And remember, because these are now taking like half the area they were, they can probably be reduced to a 300 mil pipe, like both of them. Because there's half the water going through each gully, going through that pipe than there was previously. Remember, everything downstream, though, still needs to be the 450 diameter pipe, because it is taking the full amount. So let's run that and see whether these gullies explode. No, perfect. So we just saved a bit of money there because we use thinner pipes. Hopefully we met the design standard up here of the flow width. And what you'd probably do as well, you know I said about you'd have a double gully? It might be you use one of these other inlets instead. And they can probably take more water or something. But anyway, let's check design and see what the game says. It's rejected. Oh. But you can see exactly how much everything costs. You got your gullies, your manholes, your head walls. And you can see why we failed. So mostly it's because I'm in the demo and I can't drain the rest of the map. I need the full game in order to drain this entire thing. But also it says my pipe is too shallow. Now there's something I sort of forgot about. If we turn the contours back on, there's two areas where my pipe could be too shallow. Oh, hang on. This one's spurting out water. What are you doing? Well, that'd be where my pipe's too shallow. For some reason, we've got a backdrop. That should be like down the bottom. So the inlet level there is 253.88. So if I just shove that pipe and make the outlet the same level, boosh, there you go. They're flat now. Okay, so why is this flat? I'm going to guess then, not all of my pipes have been laid at the same gradient. Have they just been laid at the 1.2 depth? Oh yeah, look, minus 1.5%. This one, minus 0.1%. Okay, so basically, the water here coming down this pipe is steeper, so it's absolutely creaming it, going real fast. If you then go to a flat pipe, which we got here, the water slows down, so you're not getting as much flow velocity through there. So your flow rate slows down the slower the pipe velocity, the flatter your pipe is. So either you've got to make this manhole up here deeper so that the water flows at a faster rate, or you've got to increase your pipe size. Generally what you do like a little cost benefit analysis. So you'd say, well, if I up the pipe size of this, it will cost this much. Or if I make this deeper but keep it the same diameter, it will cost this much. And then basically you just go with whatever's cheaper pretty much. Now look at this. It's already 2 meters deep. So I don't really think I want to go any deeper than that. Oh, actually, I don't know why I assumed everything would be like the same depth. So that could help us if we run the storm again. But yeah, it didn't. So what you'd do, you'd probably just do like a little... You'd make this slightly deeper until you work out the like shallowest it can be where that pipe doesn't surcharge. But as I'm lazy, let's just do pipe size 600. And then the one that we're actually worried about, that one, 600. And the reason you do both, you can't have a big pipe that goes to a smaller pipe because that will restrict the flow. Even if it's like a steeper gradient, you always want to have your downstream pipe either the same diameter or a bigger diameter than any upstream ones. It's just good practice. And that means like there's less chance of blockages and stuff. We'll run the storm now and then hopefully making those pipes bigger. Yes, this manhole doesn't surcharge. So if we now check design, oh no, it's gone uphill now. It's gone uphill 0.08. I think where I made the pipe bigger, it didn't actually change the head wall depth. So this pipe here, if we want to make it the same slope, so minus 0.52, minus 0.52. Oh, I didn't change. I have to put it in manually. Okay, so yeah, I've just got to move this head wall manually like that. Okay, so we want to go down to there. So that slope is the same, minus 0.52. But yeah, if we run this storm event and then check our design, yes, it's rejected, but that's only because I'm in the demo. I need more gullies. But aside from that, we fixed everything else. Cost us 100 grand to build this design. But basically, if I were to continue doing this, I'd just put my gullies at my low points. I'd then place gullies up along each of these so that that flow width doesn't exceed 1.2 meters. And remember that, so a car can drive down here without their wheel touching the puddle on the edge of the road. Then I'll just connect them all up to my drainage network, size my pipes so that the water gets downstream without manholes surcharging. And I reckon the game would say, pat on the back, Matt, you've just taught some people how to be drainage engineers. Now, my question to you, is this a game or am I just enjoying this because it was my day job, but with graphics? So, because I had an absolute blast playing this. You guys probably turned this off within like 2 minutes. I imagine to the average viewer, it's probably extremely boring. But this is literally what I did for like 10 years. So yeah, let me know what you thought. And if you have any other drainage questions, let me know in the comments. I'll try and answer them if I can. So that is literally my day job in a video game. And it wasn't a virus. It wasn't a scam. Remember, the demo's free. The game costs 150 quid. Not cheap. But honestly, you can learn as much from this as like a 10-year career in engineering. So probably worth that 150 in my opinion. Anyway, for now, I'll say peace, love, and floods. Bye, guys.